Alright everybody, we're moving forward into Chapter 8. We did the PowerPoint introduction of the kind of nomenclature, physical properties, boiling point, acidity, all that kind of stuff. So we're now moving into the chemistry, so this is more of the reactions and mechanisms and stuff of alcohols. First one is synthesis of alcohols. Synthesis of alcohols. ROH is how do we make alcohols? And there's a couple of different methods we can do this. One is via SN2, SN1 chemistry that you guys are familiar with because we just did a ton of work on SN2 and SN1, right? So if we're doing SN1 chemistry, how would you go about making an alcohol? One way is if you have a secondary haloalkane, like a bromobutane or something like that, or chiral or achiral. If it's secondary, you can do solvolysis with water. Of course, that makes this secondary alcohol. What does that mean? I went from a wedged bromide to a line bromide, line hydroxy or alcohol. What happened to the chirality? We lost it. We now have a mixture of enantiomers, right? So this is another way of saying like wedge and dash 1-to-1. So this is a racemic alcohol. This was single enantiomer. This was racemic now. So, and by not showing wedge or dash, we are indicating it's racemic. So this is just a way of saying it's not a single enantiomer anymore. It's a 1-to-1 mixture. What other byproducts do you get in an SN1 reaction? Of course, we get the E1 byproducts. That or that. Yeah. Okay. And alright, so what other ways do we know how to make alcohols from a bromide using SN1 chemistry? Of course, you can do it from a tertiary. Same way. So secondaries and tertiaries work. And okay, of course, in both of these cases, you get HBr out also. It's not a very exciting byproduct. And here we also get HBr and also the E1 product. Okay, all right. So that's all kind of now it's old news for you because you're kind of experts at SN2 and SN1, right? What about via SN2 reaction? Any ways to make alcohols via the SN2 reaction? And yes, there are. For example, if I had a primary bromide and I'm trying to, could I do a solvolysis the same way as I did up here, like H2O? And that's posed as a question. Is it a yes or no? Can you do a solvolysis on a primary? And the answer is definitely no. Why is it a no reaction? NR, no reaction. Why is it a no reaction? And the answer is because the solvolysis goes through an SN1 mechanism. SN1 doesn't work on primary, right? Because these SN1 reactions go through a carbocation intermediate. And can't do carbocations on primary, so this does not work. But is there another way to do it, like related, as definitely an SN2 reaction? Whoops, I think I messed up the carbon count. There's 3, 4, so let's just add a carbon there, and a carbon here, and 1, 2, 3, okay, cool, there we go. Is there maybe another way we could do this? SN2 reaction. What's the problem with water? Why doesn't water work? In this sort of we say SN2, but it's definitely not going to be SN2 because water is a poor nucleophile. The only way this would work up here is if it is SN1, and SN1 will not work on primary, right? How can we adjust this to work in an SN2 manner? Like maybe we can have a better nucleophile. I don't know, what do you think? What's a good nucleophile that'll do this? Think about it, just maybe put my finger right there and be like, what if I use that as a nucleophile? OH minus, like NaOH. Na plus OH minus, maybe DMSO or some polar aprotic solvent. And yeah, that'll actually work. That totally does work. This will work. But we do have a slight problem that this is it's a good nucleophile, but it's also a good base. And what happens with good bases on primary, secondary, or tertiary? You actually get some E2. So you might get something like that, right? So that's not actually perfect. It's not a perfect reaction, but yeah, you will get some of your desired alcohol product through an SN2 reaction. And the mechanism, of course, of SN2 is really simple. Circle lone pair, attack, kickoff. Okay, so it's SN2. Yeah, alright, so that is a viable reaction. We're going to see some better ways to go from a bromide or whatever to alcohol that avoid E2. Okay? Because and actually I'm gonna qualify this up top. VSN2, and then I'm gonna say primary RX. Okay? So on primary alkyl halide, can't use water because it's not a good enough nucleophile. You can use OH minus. You may have a little bit of an E2 problem because of the basicity of this hydroxide OH minus, and knowing that E2 is formed by bases, right? But yeah. So this is okay, but we'll show a better way in a second. What about what other substrates can we do SN2 on? You can do primary. What else can you do? You can do secondary, right? Okay, so we can do primary, we can do secondary. So what if we do the same exact thing and we'll just pick this secondary alkyl halide with NaOH. With NaOH and maybe DMSO or something. Alright, so will this work? I mean, it seems like it should work. OH minus, good nucleophile, kicks off the secondary alkyl halide, and you would get the primary alcohol, secondary alcohol, sorry. The problem, though, is that, again, this goes back to the basicity of hydroxide, right? It wasn't that big of a deal with primary, but once you have secondary, the basicity actually gets maybe worse, and so you also get a lot of E2. So you'll get the E2. So I'm just going to say problematic, and you're going to get problematic complicated mixture of products. Okay, so this doing the SN2 style reaction on secondary does not work because you're, in addition to getting the alcohol, you get a large amount of the alkenes, right? So with the primary, it's okay. You can still, it's a relatively minor amount of E2. These are E2. Okay, and why is this? Is this completely new, or did we have any similarity to any of the other stuff we learned about? Because this thing, hydroxide, is kind of similar to like MEO minus or something. MEO minus Na plus or something like that. And do you remember, if you look at the end of chapter 7, the last chapter, when we talked about methoxy and like ethoxy and propoxy, we talked about when would they do SN2 and when would they do E2, right? And we said back then that these things, methoxy, sodium, or whatever, on primary would do like an SN2 style reaction, and that would be kind of consistent with this one, right? But we also said that for secondary, these ones actually give a lot of elimination, and so this kind of this behavior that we're showing up here is sort of similar, and that yeah, we may get a little bit of SN2, but it's primarily E2. And a way to say this is it's not a viable method. If you have secondary, you can't really do this. Not viable method. Okay, so if you have a secondary, you want to try to do a nice little, you know, nucleophilic displacement of the bromide to make an SN2 product, you're going to get a lot of E2. So we say this is kind of bad. I might even put an X there and just say it's bad. Let's write the word bad. Okay, there we go, bad. Very bad. Okay, cool. So is there an alternate way of accomplishing this that works well on primary and secondary via SN2? And the answer is yes. We have an alternate method that avoids all of this E2 business. All of the E2 business that we talked about, this and these, can be avoided if we use this alternate method. So let's show the alternate method. Without E2. Alternate method without E2. And that is, and this works on primary and secondary. And how does it work? Okay, so I'll show an example. I'll just I'll do this one, iodide. And how do we accomplish the SN2 conversion of this iodide to an alcohol? And this is how you do it. You first use a different nucleophile, Na plus, O minus, and this is a carboxylate, right? This is like the sodium salt of a carboxylic acid. This is a carboxylate. Carboxylate of acetic acid, because acetic acid would be that with a OH, right? That would be acetic acid. Carboxylate is the sodium salt of it, right? And maybe some DMF. Okay, is this basic? The way this is basic? No, this is like a gazillion times less basic. This is actually a very non-basic. Good nucleophile. Great nucleophile, not basic. When you have a really good nucleophile that's not basic, and maybe a secondary substrate, and maybe DMF is your polar array product solvent, this is a very easy reaction. This is a simple SN2, right? No elimination, no E2. So you get a nice conversion to the SN2 product. Oxygen, okay. The problem might be, oh, well, we didn't want an ester. This is an ester, right? We want an alcohol. That's the chapter 8's about alcohols. So the question then is, can we convert this to the alcohol? And we can, and that's why this actually works out, this alternate method. We can convert this, we can basically wipe off the ester and just leave us with the alcohol, which is the OH version, right? And that's with the second reaction. And the funny thing about this is that now we use NaOH, and maybe water, which is exactly what we just used above, problematically, right? Because this was an SN2 and an E2 reaction. This, though, is not. This is not an SN2. Let's just draw the product. Alcohol, and you get acetic acid out, parentheses. The acetic acid is irrelevant. It's not part of the, you know, we can separate that out, remove it. you might have the question of, well, oh, if NaOH is bad here, which it would be bad here because it would give you E2, why does this work? Now this actually jumps ahead into organic 2, the mechanism. So we're just I'm gonna give it a name, but we're gonna skip it because this is technically organic 2 stuff. The name of it is called Nucleophilic Acyl, ACYL, Nucleophilic Acyl Substitution. Abbreviation might be NAS, maybe, yeah, NAS. Oops. And this is chapter 20 in the book, so this is a little bit later, the mechanism of it. You will learn about this in organic 2. But for now, we can use it as a method, as a reaction, without caring about the mechanism, because we don't want to jump ahead to an organic 2 mechanism. Alright? Basic point though, if you want to convert a primary or secondary alcohol, primary or secondary halide or mesylate or triflate or tosylate to the alcohol, you first do an SN2 with this stuff. It's a carboxylate. There's one other name for this one, is called sodium acetate. Sodium acetate. That's the full name of the molecule, sodium acetate. But it's just a very simple SN2. Kicks off the iodide, and then you're left with an ester. And then we're cleaving the ester. We cleave the ester with sodium hydroxide, not via SN2. So there's no elimination. All the elimination business is gone. And this thing is called nucleophilic acyl substitution, or NAS. And this organic 2 reaction. But, so we can use it without knowing about the mechanism. You'll learn about the mechanism of organic 2. Alright? One other thing I was going to mention, maybe from before, why do I say number 4 here as my kind of section heading? And that's because the previous Chapter 8 stuff was in the PowerPoint. Those are like 1, 2, and 3, which were the nomenclature, physical properties, etc. So that's why we said number 4 here. All right. Okay, now we're on number 5. So number 5 is synthesis and reactions of alcohols. ROH alcohols, oxidation and reduction reactions. Oxidation and reduction. Oxidation and reduction. This is a different class of reactions that create alcohols, or reactions that kind of change alcohols into other functional groups. So what's the meaning of these words? Meaning of oxidation reduction. And also sometimes we abbreviate oxidation reduction as bracket O bracket. And what do you think the other one's going to be? You'd probably say bracket R bracket, but it's actually bracket H bracket. Because we're actually adding, by reduction we usually add hydrogens to the molecule, and that's why we say bracket H bracket. So the abbreviations are bracket O bracket, bracket H bracket. Alright, so oxidation occurs. There's a couple ways you can kind of identify an oxidation reaction. One, when there's an increase in number of bonds to atoms that are more electronegative than carbon. And what are some of these atoms that are more electronegative than carbon? So it could be like oxygen, nitrogen, sulfur, chlorine. So if you have 0 bonds to chlorine, then you have 1 bond to chlorine. We've seen that before, chapter 3. That's also considered an oxidation. But if you're increasing the number of bonds to these atoms, it could be either from 0 to 1 or 1 to 2 or 2 to 3. All of those are considered oxidation reactions. Oxidation occurs when you increase the number of bonds to oxygen, nitrogen, sulfur, chlorine. Another way to see it, and sometimes both of these happen, is you can either increase the number of bonds to one of these, or you can decrease the number of bonds number of CH bonds, the number of CH bonds. So if we have 3 bonds to CH and you get 2 bonds to CH, that's also considered oxidation. So often we see both of these things simultaneously. Okay, and the reduction, definition of reduction is the opposite. So reduction occurs when you decrease the number of bonds to all of those elements up there, electronegative elements, oxygen, nitrogen, sulfur, chlorine, etc. So you decrease the number of bonds to those things. These are the typical ones, and of course there's others. That's considered a reduction. Or another way to envision reduction is increasing number of CH bonds. Okay, cool. So now we're going to show a couple examples, just general examples, emitting the reagents and chemicals that cause these reactions. Let's just show a couple examples. All right. So example number 1. Example number 1 is if you, we're going to consider methane, and methane can be oxidized all the way up to CO2, carbon dioxide. So let's just show the kind of steps of oxidation as you go from methane all the way up to CO2. Alright, so let's just draw methane. What's methane? CH4. Okay. So you can envision an oxidation event where methane, and I'm just going to draw equilibrium to just show that these are, you can kind of go one direction or you can go the other direction. We can oxidize, bracket O bracket, methane to methanol. Right? And if you go the opposite way, if you go from methanol to methane, that would be formally a reduction. Okay? So far so good? Now, what would you get if you keep going? If we oxidize methanol, what would it be? Knowing the rules for oxidation, it's like increasing number of bonds to oxygen or decreasing the number of bonds between C and H. What would it be next? If you oxidize methanol, you would get formaldehyde. From 1 bond to oxygen to 2 bonds to oxygen. That is the next oxidation state. We went from this oxidation state to this oxidation state. Now, with 1 bond to oxygen to 2 bonds to oxygen, now we're at formaldehyde. If you go from formaldehyde, you can go back down to the alcohol by reduction. And there's reagents that accomplish these things. We're not going to talk about the reagents quite yet. Alright, so alcohol aldehyde, specifically this molecule is called formaldehyde. Formaldehyde. Okay, what if, can we keep going? Yeah, we can totally keep going. Oxidize from 2 bonds to oxygen to 3 bonds to oxygen. And we can go backwards too. What do you get if you oxidize from 2 bonds to oxygen to 3 bonds to oxygen? What functional group do you get? Oh, what's this? 3 bonds to oxygen. What is that? What functional group is that? That's a carboxylic acid. Okay, and specifically this is called formaldehyde. What's this specifically? It's something acid. Formic acid. Alright. Can we keep going? Any higher? Anything higher than 3 bonds to oxygen? Do you know any molecules with 1 carbon and 4 bonds to oxygen? Here's 3. 1, 2, 3. And yes, you can keep going. One more step. Bracket O, bracket, bracket H, bracket, going the other direction. And of course, what's the molecule you're probably familiar with that has 4 bonds to oxygen? And that's carbon dioxide. Carbon dioxide, CO2. Okay. Alright, so what we're going to learn, like the different reagents and mechanisms to accomplish some of these reactions. Not all of them, but part of that is an ongoing process. But we will learn these things, okay? Alright, so the second example will be a little simpler. Rather than considering the full oxidation of methane all the way up to CO2, let's just consider like what the oxidation states starting from a primary alcohol. Okay, and let's think about these. So here's a primary alcohol. Can that be oxidized? I'm going to draw the oxidation reaction and reduction reactions a little differently in this case. I am going to do it like this, and I'm going to say, can we oxidize a primary alcohol to something higher, and what would it be? So if I can oxidize the primary alcohol, what do I get? If I have 1 bond to oxygen, what do I have if I have 2 bonds to oxygen? And what's the name of the functional group? You know what that is? It's an alcohol. What's this? It's one of your functional group names that you've long forgotten. It's called an aldehyde, right? So that's an aldehyde. Can we take that aldehyde and oxidize it to something higher? And the answer is yes. What if you go from 2 bonds to oxygen to 3 bonds to oxygen? What would that be? Look up there. 3 bonds to oxygen. It's a what? It's a carboxylic acid. So the same thing here. Yeah, you can go to a carboxylic acid. So this is like the normal progression. If you have a primary alcohol, you can go to the oxidize to the aldehyde. Aldehyde can be oxidized to the carboxylic acid. Okay. Can you go the other way? Yeah, you can. Now there's some technical problems with some steps are difficult. It's actually kind of difficult to go from a carboxylic acid directly to an aldehyde, and we'll explain that in more detail as we go along. So this step is actually impossible. The other steps are totally possible. It's easy to go from a primary alcohol to an aldehyde, aldehyde to carboxylic acid. We can go from, if you have an aldehyde though, you can go down to a primary alcohol, and that is a bracket H bracket. That's a reduction. That is a very easy reaction, as we'll see. And you can also go from the carboxylic acid all the way down to a primary alcohol. That's also possible, and that is a reduction. So there's a couple steps that are possible, and you know, we'll go through all the detailed mechanisms and reagents and reactions in a second. All right. Let's just consider a third example. I'm going to sneak it down at the bottom here. Example number 3. And that is if you have a secondary alcohol. What are the kind of steps for a secondary alcohol? Secondary alcohol is even easier, maybe, than the primary alcohol. Because if you have a secondary alcohol, and I'll just draw like that as our secondary alcohol, what is the higher oxidation state of a secondary alcohol? The higher oxidation state, if you go from 1 bond to oxygen to 2 bonds to oxygen, what would that be called? Not an aldehyde, but a, think of your functional group names, begins with K, ends with ONE. It's a ketone. So this is an alcohol to a ketone. I'm just going to kind of sneak in, yeah, you can oxidize that. That's an oxidation, right? Alcohol to ketone is an oxidation. Could you possibly reduce the ketone? Yes, you can do that too. Okay, cool. So that's all I want to say for that. And so this shows everything again, and we stepped through them all. With methane, it's complicated because you have a whole bunch of different oxidation states, all the way up to carbon dioxide. Primary alcohol is a tad less complicated. You have primary alcohol, aldehyde, carboxylic acid. Some of the reduction things are not possible. You can't go from a carboxylic acid to an aldehyde. You can go from aldehyde to an alcohol. You can also go from carboxylic acid all the way down to an alcohol. And we'll learn all of these methods very shortly. And then if you have a secondary alcohol, you can do a one-step oxidation to ketone or a one-step reduction to the secondary alcohol. Alright, so continuing, and we talked about, we're in the sort of oxidation reduction section, and let's get into specifically reduction. Reduction of C double bond O. So what are the different ways we can reduce a C double bond O, like a ketone or aldehyde? So when we say C double bond O, right now we mean ketone and aldehyde. Alright, and the ways we do this are with things called hydride reagents. Hydride reagents. What's hydride? Remember hydride? You ever heard of that word before? If you actually have heard about it, you've probably forgotten it. Hydride means H dot dot minus. Definition of hydride is H dot dot minus. What's H plus? You know, what's H plus called? Proton. So hydride is totally 100% opposite from proton. A proton doesn't have those electrons. So this is a kind of unhappy, sort of unstable, reactive thing. Okay, so what's a hydride reagent, and what are some of the kind of ways we can use these to do reductions? So first, I'm going to show two ways. One way is if we have a ketone, for example, it works for ketones or aldehydes. And we're going to, there's kind of like two reagents, and we'll go through them both in detail. The first one is NABH4. We usually do this in ethanol. Ethanol or ETOH, or methanol works also, but like a alcohol, right? And what did that do? It converted our ketone to a secondary alcohol. Okay, it's a reduction. We're going from 2 bonds to oxygen to 1 bond to oxygen. It's a reduction. All right. The other way we can do this is a different hydride reagent. I just want to say that this is a ketone, but it's also for aldehyde. Aldehyde, of course, is the ch version of this. This is also aldehyde. Okay, so the other way we can do this is a two-step process using a different hydride called LiAlH4. Here it's NABH4, here it's LiAlH4. There's usually a different solvent. The solvent up here is ethanol. Here it is usually something called THF or ether. THF or ether. I'll draw THF and ether in a second. Okay. And then you have a second step, which is H2O or H3O. Okay, so it can either be water or slightly acidic water, and essentially this does the same thing. These have very nice mechanisms. I'll show those in a second. So your end products are in this case, the secondary alcohols. If you used aldehydes, though, it would be primary alcohol, right? If I had that's like kind of an aldehyde. If I had that as an aldehyde and I got that as a product, you'd say, oh, it's a primary alcohol, right? So it's either secondary alcohols or primary alcohols, depending on what things you're reducing. Okay, what are THF and ether? Let's just draw what I mean by that. THF, what's THF? It's this. It's just a 5-member ring with oxygen. It's also called tetrahydrofuran. Tetrahydrofuran. It's a cyclic ether. Ethers are really, really stable and to reactivity, so it's a nice stable inert solvent. It doesn't react like with the hydride. Okay. Ether. When I say ether, what I really mean is diethyl ether. Ether is that. And ether is kind of a sloppy abbreviation for diethyl ether. It's the most common ether. It's probably made on multi-ton scale every year in the United States. It's a nice inert solvent, really flammable, really it'll catch on fire very easily, so you have to be very careful and not have open flame like in the laboratory. I think I showed in chapter 2 the little Back to the Future cartoon with all the little flames coming out of the car, and as it shoots off into a time portal. And that was filmed using ether for its flammability as a kind of like a stage prop in a movie. Tetrahydrofuran is also really flammable, but both of these we can use them safely in the laboratory. It's not that big of a deal. Just don't have a Bunsen burner going with your ether or THF. Okay, so those are the two these are like general examples, and we'll go through the mechanisms in a second. Couple examples. I don't know, we'll just draw some random aldehyde, and I will react it with NaBH4 ethanol. What do you get? Is a reduction, so it goes from the aldehyde to the primary alcohol. So, I mean, you can kind of envision that by just envision, you know, what happens if you have one less bond to oxygen. So you went from 2 bonds to oxygen down to 1 bond to oxygen. It would be a primary alcohol. So it would be that primary alcohol. Okay, I'll show the mechanism in a second. For fun, let's just draw a ketone. Not only one ketone, let's make it even more fun. Let's make it a diketone. And we're going to now react with lithium aluminum hydride. And for reasons we'll explain later, this becomes a 2-step process. So it's a 1,2. Lithium aluminum hydride. And maybe H3O plus, or it could be H2O as a second step. What's the solvent for lithium aluminum hydride? It's, pick your choice, THF or ether. We'll do THF. Okay, and what do we get? We're going to assume, and you can pretty much always assume in this course, like if you have 2 functional groups and you have a reactive reagent, that you're always going to use excess. Assume excess, so there's going to be excess. It's not like you're only going to react with one of these, you're going to react with both of them. So both secondary alcohol, so both ketones become secondary alcohols, right? And now you have the ketones are converted as secondary alcohols. So these are kind of real examples of reduction of either an aldehyde or a ketone. I should say that I sort of pick these reagents arbitrarily. So like NaBH4 ethanol would also work for this diketone with 2 ketones, just as well as this aldehyde would work with these reagents, lithium aluminum hydride and H3O, and that would give you the same primary alcohol product. Okay? Alright, so let's show the mechanism of these reactions. Well, we'll show both of them, NaBH4, LiAlH4. They're very similar, they're related. We'll first do NaBH4. Mechanism. I mentioned that index cards might be a good way to kind of keep all these reactions straight, and I would probably have an index card for the NaBH4 reaction. I'd have an index card for the LiAlH4 reaction, and they're related, so they'd be in the same kind of pile, or group them with a paper clip or something. Alright, so let's do the NaBH4 reaction. So NaBH4 is kind of what we're going to call nucleophilic H-. It's called nucleophilic H-. And what do we call H-? It had a word, hydride, so you could also call it nucleophilic hydride. H-, definition of H-, H dot dot minus is hydride. Okay, and yeah, so let's do an example reaction and then what the mechanism is. So if we have we'll just draw a ketone. And it could be a ketone, it could be an aldehyde. And we're reacting this with NaBH4 ethanol. I'll draw out ethanol this time. Ethyl alcohol. What's the product? So well, let's go through the mechanism first. All right. So first thing about the mechanism is we gotta draw BH4 out. The Na plus is not that big of a deal. The BH4 though is a big deal. It's B H H H H. Okay. And the charge is negative on boron. Okay, and what's the counter ion? It's sodium, right? So we draw maybe a sodium up here. The Na plus is not that big of a deal. Okay, so that's what NaBH4 looks like. It's Na plus, BH4 minus. What I'm going to do is I'm going to say that this is relatively equivalent to H dot dot minus. H dot dot minus, okay? So it's relatively equivalent to hydride, H dot dot minus, okay? And I'm also going to say that this is slightly simplified from the book mechanism. Simplified from the book mechanism. The book does this slightly differently, but I'm happy with my simple mechanism. So if I ask you for a mechanism, you can either use my mechanism or you can use the book mechanism. It's all the same. You know, they're going to be subtly different. So what is this H dot dot minus going to do? It's nucleophilic. It says nucleophilic hydride. So nucleophiles do what? Nucleophiles attack stuff. What's it going to attack? Well, and what carbon might be labile for attack? If this is delta minus and this is delta plus, the carbon is delta plus. What do you think is going to happen? H minus sees delta plus. What's it going to do? As a nucleophile. What do nucleophiles do? It's going to attack it. So circle it, attack it, electrons go up. Okay. We just did the reduction. That was the reduction. What do you get mechanistically? Well, the way I like to draw this, I'm going to just go ahead and draw the product here. Okay. There's the secondary alcohol. But this is actually a two-step process. This is going to be step one, and then we have a second step. So let's go downward and we'll draw the intermediate. What happens when H minus attacks the carbon? It forms a bond, covalent bond. Now we have carbon with a negative charge. There's our new H. Question is, where do we get a proton from to finish the reaction up? And I don't know, do you see any sources of proton anywhere? We don't have any acid around. We don't have like H3O plus. We do got some ethanol, so that's going to be our proton source. Okay, so we draw a little bit of ethanol. If you want, you could just snag this proton, or we can snag this proton, whatever you want to do. How do we grab a proton mechanistically? Circle on pair. Grab the proton, and look at that. We just did the full mechanism for how NaBH4 works to reduce ketone to a secondary alcohol. Okay? Now we're going to see that the one for lithium aluminum hydride is basically the same. Is there a counter ion for the O minus? There is. We often just omit it, but I'll just draw it in this case. So something with boron. The boron actually has like a counter ion. We can call it BXN plus. Okay, so BXN is just like various things around boron, and has a positive charge. So there's kind of like a ion pair between this O- and the BXN plus. Sometimes you'll just draw sodium because sodium is still around too, but that's not really a big deal. Okay. Okay, so we have this counter ion pair, and then we have a secondary alcohol product. I'm going to quickly show the book mechanism. I'll show briefly the book mechanism, just for contrast. And you're welcome, if I ask you for the mechanism, you can draw whatever you want. I think my mechanism is really easy, just H-, right? H- attacks, and then you grab a H+. But here's the book mechanism. Ketone, alcohol, NABH4 ethanol. So the way the book draws, it's slightly different. Oops. They just draw BH4 kind of like that, negative charge, Na plus, like that. And then what they do is, rather than show like a free version of hydride, just go attack, they just sort of take this bond and attack. And it attacks the ketone and the electrons go up. So it's not that different. I just like showing it sort of as a nucleophilic hydride, like a kind of like free H-, even though this mechanism is probably a little more correct. Okay, then we have O- and then BX form, or BXN, BXN negative. So that's just some boron with some stuff around it and a positive charge, plus, plus, plus. O-, boron plus, and then just grab the proton, and you're done. Okay, so that's the book mechanism. I just sort of show this kind of free, the idea of this being a free hydride, an H-. Okay, let's show the mechanism now of lithium aluminum hydride. Sometimes the abbreviation is LAH, lithium aluminum hydride. It's going to be very similar. This stuff, though, we're going to say it's considered more reactive than NABH4. Is that a good thing? Is it a bad thing? Well, there are times when you can accidentally catch your lab on fire by, this stuff's really reactive. It will catch on fire very easily if you're not careful, and that's a reason that people sometimes avoid using it, right? NABH4, this stuff is actually pretty well behaved. We actually use this in chem233, the organic 2 lab. We use it to reduce a ketone, and it's less prone to catch on fire. Sodium or lithium aluminum hydride is kind of hazardous and reactive. So usually, if you have the choice, you'll just use NABH4. On rare occasions, this stuff you got to use lithium aluminum hydride because it's actually more reactive. Certain functional groups will not react with NABH4. certain functional groups will not react with the mild stuff, so you get the big hammer out, which is lithium aluminum hydride. Okay, so we'll talk about, you know, the various uses of these in the future. For now, just consider it an alternative. It's just, practically speaking, we'd probably avoid using lithium aluminum hydride unless nothing else works. Okay, but the mechanism is really easy. We can do the mechanism without catching the paper on fire. So let's try the mechanism. This time I'll draw cyclohexanone randomly going to the secondary alcohol. And we'll use lithium aluminum hydride. Remember, this is a two-step process. Lithium aluminum hydride and then H3O plus or H2O is the second step. And what's our solvent? THF or ether. We'll just do THF. Cyclic ether. Okay. And mechanistically, we're going to make that same assumption of just, you know, AlH4 minus is basically H dot dot minus. H dot dot minus. Okay? So AlH4 minus is kind of like a free hydride. We can call this a, you know, this is a simplification of the mechanism. We're just like, oh, well, that's going to be a free hydride. It's going to be mechanistically a free hydride. Okay, and then what do you think happens? Delta minus, delta plus. What happens? What's that H minus going to do to the delta positive carbon? It's going to attack it. Very nicely. Now we have a O minus thing. We actually gave these names, remember? Chapter 7. When you have it looks like an alcohol, but it's the negatively charged version. The O minus, we call them alkoxides. So this is an alkoxide. Just like we talked about, like sodium, or like methoxide, MEO minus was also an alkoxide. This is totally an alkoxide. The counter ion, we're just going to say it's AlX4 plus. We often just omit the counter ion because it's not that big of a deal. Sorry, it's AlX, and we're just saying some number of things around the aluminum. Okay? Then the question is, what is going to be the proton source? Where's that proton going to come from? Well, THF does not give up protons. That's why we have the second step, the H3O plus step. So first step is H minus, second step is H plus, which is essentially H3O plus. So circle lone pair, grab a proton, kicks on the oxygen, and you're done. First you do H minus, then you do H plus. This is essentially H plus, right? H3O plus is essentially H plus. Okay, that's pretty similar to the way NABH4 worked. The key difference is that with NABH4, it was the ethanol that served as the proton source at the end. Okay. We talked about ether and THF. The lithium aluminum hydride, LiAlH4, is usually done in aprotic solvents. Aprotic, so things that don't have a proton donor. The typical ones, like we said, were diethyl ether or THF. Okay. We cannot use ethanol for lithium aluminum hydride, because that will actually cause a big fire. Big, 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 big fire. So the whole lab will burn down. Potentially. It's a very, very dangerous. That's why we said this stuff is really sensitive. You have to be extra careful with it. Ethanol would almost guaranteed cause a big fireball when you use it. I'll show why ethanol is kind of bad for lithium aluminum hydride. It is okay for sodium borohydride. All right. Let's just draw. I'll just sneak it underneath here. Why is ethanol bad? So say we're all out of THF. We're all out of THF, and we're going to try to use lithium aluminum hydride and ethanol. We're all out of THF. We try this, and I claim your lab will catch on fire. And indeed, you know, lithium aluminum hydride is H minus. So you want it to go attack the ketone, right? You're like, oh, this should go attack the ketone. Delta minus, delta plus. Right? Delta minus, delta plus. You want your stuff to go react with the ketone. But instead of doing that, this stuff is very basic, and it sees this OH, and it just grabs it instead. Okay, so this actually does not do what you want it to do. It does not do this. Just put an X there. It actually reacts as a base with the ethanol, and that's why ethanol is going to be bad. Because once that happens, what do you make? What happens when this reacts with that? You make H2. You make H2. You make a lot of heat. Lots of heat. You can imagine what happens if you make a bunch of H2 and a bunch of heat. What happens to the H2 in the presence of heat? Big fire. Okay? And so that's why we have to be picky with our solvent choice. We usually use THF or ether, which are not hydrogen bond, or not hydrogen donors, right? They don't have OHs the way ethanol has an OH. All right, so that is a summary of why we would rather use THF or ether. And then we have a second step with lithium aluminum hydride. We have a second step with H3O, which is usually done very carefully and slowly to also avoid fires. So this is done separately. Okay, and that's why we don't use ethanol for lithium aluminum hydride. So a good way to avoid fires, like actually working in the laboratory, is really not using lithium aluminum hydride unless it's absolutely required, and you also need kind of specialized training because it's a little dangerous and has fire potential. So usually speaking, you would just use NaBH4 and ethanol, and there's no problem, and this works really well. Another example. Let's say we do this differently, and I say, here's NaBH4 and ethanol, and you're making this alcohol. And the question isn't what the product is, but what the starting material is. Like, what thing over here would react with NaBH4, a reducing agent? It would reduce something to give this secondary alcohol. Would this be a ketone? Would it be an aldehyde? Would it be something else? You know, on the exams or quizzes, I usually tell you the molecular formula, but this time I'm not. Well, you just think, like, if this is one bond to oxygen, what would be the thing over here that has two bonds to oxygen? It would be the ketone. So redraw this, but as a ketone. So we'll draw this like this. You know, this is what we're trying to figure out. And it's like, yeah, the ketone would be the thing in the box. So how do you draw a ketone? That would be reduced by NaBH4. It would be like this. Okay, so that's actually what we just showed is actually synthesis. So the idea of like figuring out what a starting material is for a reaction. We're going to do tons of this. We'll get back to this in a bit also. Alright, now we're on to, I think it's 5C. So oxidation and reduction, and C is actually moving away from reduction to oxidation. Oxidation of alcohols. Oxidation of alcohols. And we're going to talk about chromium reagents. Chromium reagents. And when, you know, in basic organic chemistry, as you're learning about it, you associate hydride reagents with reduction, chromium reagents with oxidation. Okay? So all of these reagents have high oxidation state chromium. High oxidation state chromium. So it's going to be chromium with a bunch of oxygens around it and stuff like that. High oxidation state chromium. So the typical high oxidation state chromium is chromium 6. That's going to be the magic number for the reagents. They're going to be like 6 bonds to oxygen and electronegative atoms. 3 reagents to know about. Okay, with interesting structures. So the first one is chromium, double bond O, double bond O, Cl, O minus, so far so good, yeah? O minus. And then we have this crazy thing over here. It looks like a benzene but with a nitrogen. It actually has a proton on it also. What is the charge on nitrogen if you have 4 bonds to nitrogen? It's plus. So that whole thing is positively charged. This is negative plus, so this is a complex. These things is complex. We're just going to put a bracket around it. All right. This stuff is called PCC. PCC. The name of it, what PCC stands for is, well, this is called pyridine. That's called pyridine. Pyridine. If you have the H on it and the plus charge, it becomes pyridinium. 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 And this thing is a weird chlorine with chromium thing, and it's called chlorochromate. Pyridinium chlorochromate, okay? And the abbreviation is PCC. So you're going to see PCC 1,000 more times, all the way through the end of Organic 2. So you don't need to memorize the structure, but you will need to understand what its reactivity is, okay? I'm also going to say that this causes a partial oxidation. Partial oxidation. Okay, what does it contrast with? There's PCC, pyridinium chlorochromate. So this contrasts with CrO3. This is an easy one, right? CrO3. CrO3. Or chromium trioxide. Chromium trioxide, CrO3. Okay. And this, the book kind of emphasizes a different structure, a different chemical. So we'll just draw it out. I don't like drawing complicated things, but you gotta do that occasionally. So it's chromium, oxygen, chromium. Double bond O, double bond O, double bond O, double bond O, O minus Na plus, and then O minus Na plus. Okay? Crazy structure. But these basically do the same exact thing. And this is a complex, and it's the molecular formula of it is Na2 Cr2 O7. It's also called sodium dichromate. Okay. These, oh yeah, what's this called again? Chromium trioxide. Chromium trioxide. That's an easy one, right? Which one do I like to emphasize of these two things that are basically the same? I emphasize the easy one, CrO3, because you know, it's easier to draw, it's easier to understand the structure. The actual structure might be a little more like this, whatever. CrO3. All right. Now, if the PCC is a partial oxidation, this is a full oxidation. Okay, and so we're going to see a difference in behavior between PCC or like CrO3. If you're reading the book, they're going to talk a lot about Na2Cr2O7, sodium dichromate, but it essentially does the same thing as CrO3. Okay. So I'm going to just show the 3 basic situations, then we'll be done for this lecture. So we're still on 5C, so this is about oxidation. And there's 3 situations, and we'll go through the mechanisms and everything next time. There's kind of 3 situations you should be aware of. If you have a primary alcohol, you can do a single oxidation, or we talked about partial oxidation, right? With, what was the partial oxidizing agent? 3 letters, PCC. And what's the partial oxidation of an alcohol, of a primary alcohol? It was what functional group? Aldehyde. So this is the partial oxidation. Alright? That's what we said. PCC is a partial oxidizing agent. You get the single step oxidation as opposed to a double step, which would be a carboxylic acid. Alright, and then if we have a primary alcohol also, we can also do a double oxidation. And what did we say was the oxidizing agent that gives, it's like a full oxidation. It's not PCC, but it's CrO3 in acid, H3O+. Now the book mentions Na2Cr2O7, does the same thing. End result is a double oxidation to the carboxylic acid, right? Or we'll say full oxidation. Okay. And what's our third situation? If you have a secondary alcohol, it's going to be a single step oxidation. To the ketone. We'll call this partial also. And which one should we use? Or does it matter? PCC will always just give you a partial oxidation, like a single step oxidation. CrO3 does a 2-step oxidation. For a secondary alcohol, it doesn't matter. You can use PCC or CrO3. PCC or CrO3. Now the CrO3 requires acid water, so PCC does not. So anyway, that's CrO3 requires acid water. Okay. All right, and that, so for secondary, it doesn't matter. You can use PCC or CrO3, and it's a partial oxidation. There's no way to do like a two-step oxidation of a secondary alcohol, at least for the time being. There will, you know, chapters and chapters away, we will learn a way to over-oxidize this. It's hard for you to think about what it could oxidize to. You know, what's higher than a ketone with 2 carbons on both sides. You'll see that later in the course. Okay, so yeah, and I'll just say anywhere, anytime where we use CrO3, you can use Na2Cr2O7. Which one's easier to memorize, CrO3 or Na2Cr2O7? I think CrO3 is easier to memorize. Okay, but in all cases, they both require H3O+. All right, I think that is it. Maybe I'll just show one example, a real example. Okay. PCC. What's the product? What's the product? PCC would make a ketone. Okay. We'll show a bunch more examples next time, but yeah, this is just an example of PCC oxidizing a real molecule. All right.